wrote Heinz theorem up there, and I took the Lebesgue number definition from Wikipedia, just kind of just have a nice definition up there. If a metric system x of d is compact and open cover, x is given, then there exists a number delta greater than 0 such that every subset of x of diameter delta is contained in some number of the cover, and the delta here is your Lebesgue number.
So couldn't it be less than delta? If the diameter is supposed to be less than delta. I think you have to actually shade just a hair less than delta to make sure that that works. But okay.
That's the definition of Wikipedia. I did find one book, so
Okay.
Okay, so here we're going to prove the Heinz theorem, assuming the Lebesgue number exists. So we're given that our function is continuous on AB, and then we have a Lebesgue number. So I decided for each t, so I kind of went with the same, like the same approach as we did in class, where we're going to have like an interval, and we're going to have a smaller, our stuff's going to be in a smaller interval. So for each t in A and B, there exists a delta in t such that t minus x is less than delta epsilon t. Then our f of t minus f of x is going to be less than epsilon over 2. So if we do this from the triangle inequalities, if x and y belong to the interval, and our interval for I and t there is t minus delta over 2 epsilon over 2t, t plus delta over 2 epsilon from 2t, then we're going to have f of y minus f of x is less than epsilon, and same triangle inequality we did before. Okay? Well, if it's right, I can email it.
Something. No, it's not. It's right. It's right. Can you draw us a picture?
So kind of what we're like, we're going to be going for is there, same kind of thing as before, like we're going to have x and y here somewhere, and we're going to have our t. And what we're trying to do is we're trying to show that our x and y are in here. And when we have the Lebesgue number, it's going to show that it's all going to kind of smush together, that the subsets are going to be in each other, and that the cover, since we kind of don't have to prove the cover because we have the Lebesgue number, this was my understanding.
So x and y are closer together than the whole thing. So they have to be in some member of the cover, which is it.
Right, that's what I was hoping.
Yeah. Oh yeah, that's the point of the theorem. So they're together.
Right. So I'm going to say we have let delta greater than 0 be our Lebesgue number for the cover of our interval, IT. Which is in AB. If x and y are points in AB such that x minus or y minus x is less than delta, then both x and y belong to this new interval, which what we're kind of trying to say is that we have this interval around x somewhere, and then it's inside our other interval.
The covering set is the t minus delta over 2, t plus 1. And then you got x was in there, and then since x and y are within delta of one another, then they're inside that covering there.
Right. So since our intervals inside is a subset of our cover interval, the IT, therefore our x and y are less than epsilon.
The function at x and y. Yeah, that's it. That's the so it shortens the proof I gave you last Thursday. Considerably, you start out with knowing big number. I'm not sure, I've never read much of what LeBay did in this area, but obviously he had a hand in the formulation of the package as a general concept, because the idea of an arbitrary cover being reduced to a finite subcover is called the LeBay, Borel-LeBay criteria. So get something moving. And I imagine that was, when they were developing those ideas, the idea of a LeBay number popped up. Does every cover have a LeBay number? Only very special situations, right? An open cover, an open set, that have an open.
So, but I think
You need a compact set function. So the thing is, if you have an open cover of a compact set, then there exists a LeBay number for the cover. But if you have a non-open cover or a non-compact set, anything can happen.
So I would say also that if something's uniformly continuous, it always have a big number.
No, I'm not sure about that. Let's see. You can have uniform continuity on an open set. If you think of an example where you have uniform continuity on an open set, how about a non-constant function on an open set? If the function is continuous on the closure of the open set, I think it would be uniformly continuous on the open set as well. You get it? No, it is the point figure. You have an interval, and you strip the endpoints off constant open set. And you have a function defined on the open set. That's going to be uniformly continuous on the open set. The extension of the function to the closure of the interval is also uniformly. See, the problem is the function of 1 over x, when you can't do anything about 0, and you can't do anything about 0. Yeah, there's a lot of very subtle details. That's good. So what's uniformly continuous again? What's the definition of that?
I think right here, but
A function f on set E of real numbers, subset E of real numbers, is uniformly continuous precisely when
f of x minus y is less than epsilon x minus y is less than delta.
absolutely less than delta. That's it. You would phrase it like this: given or preassigned epsilon greater than 0, if there exists a delta, which in general depends on epsilon, but not on any point. That's the idea of it. Just depends on epsilon. Then, if the absolute difference of x and y is less than delta of epsilon, that implies that the absolute difference of f evaluated successfully epsilon. So that's uniform. There's an even stronger continuity called absolute continuity. Well, absolute continuity is a generalization of uniform. That was good. Thank you very much. Absolute continuity is being able to have the sum of intervals of x, the absolute sum, be less than delta. And that induces the absolute difference of the function over every one of the constituent finitely many of them in sum is less than epsilon. So if you only took one element in your sum on each side, that would be uniform continuity. Because absolute continuity means you're able to chop up into any finite. You take preassigned epsilon, and then there must be a delta such that if you don't pick absolute differences between any number of points, and as long as the lengths don't add up to more than delta, the differences, the variation in the function, absolutely, over each one of those intervals can't add up to more than epsilon. So it's like having uniform continuity happen finitely many, but perhaps many, many times, right? You have a constraint on x, and you have a constraint on f of x. You can chop this up into different places. And it turns out the condition for Lebesgue integrability depends on absolute continuity. And absolute continuity implies uniform, but not vice versa. I can't, on the spur of the moment, come up with a counterexample for a function that's uniformly continuous, but not absolutely continuous. But it's out here. That'd be. Oh, very often you just kind of think about weird functions and come up with. Oh, that's it. Yeah, sure.